Welcome, this is Professor Ridge. Today's lesson 8.3, the parabola. Our first learning objective for today, graph parabolas with vertices at the origin. Okay, in the ellipse, we saw that an ellipse is formed when a plane cuts through a right circular cone. If the plane is parallel to the edge of the cone, an unbounded curve is formed. This curve is parabola. Okay, so again, if we cut it where the plane is parallel to this edge, or the other edge, doesn't matter which. So just to the edge, you cut it, the cross section would be a parabola. Okay, like the ellipse and hyperbola, the parabola can be defined by a set of points in a coordinate plane. Okay, a parabola is a set of all points, x and y, in a plane that are the same distance from a fixed line, called the directrix, and a fixed point, the focus, not on the directrix. Okay, so if we look here at this figure, all the points on this parabola are equidistant to the focus. So if I measure that distance, and then I measure the distance to the directrix, those are going to be equal to each other. Okay, so that distance and that distance are equal to each other. All right, let me erase this. All right, in quadratic functions, we learn about a parabola's vertex and axis symmetry. So back in chapter 5, we talked about it in the context of a quadratic equation, quadratic function. Now we're going to think about it as a conic section and identify other key features of the parabola. So we have the axisymmetry that we mentioned before, but now we have these new terms, directrix, okay, and a focus, vertex, that's still. And then there's this thing called the latus rectum. So the line segment that passes through the focus and is parallel to the directrix is called the latus rectum. The endpoints of the latus rectum lie on the curve. Okay, so it's this line segment where the endpoints of that line segment, so this line segment goes through the focus. It's parallel to directrix. So this line and this line, directrix, latus rectum. Oh, the latus rectum's a line segment, right? Because it's just a portion of the line. So the endpoints are on the graph, and that line segment is parallel to the directrix, and it has to go through the focus. Okay, and that's called the latus rectum. Funny name, but that's what it's called. By definition, the distance d from the focus to any point on the parabola is equal to the distance from P to the directrix. Okay, so that's what I just drew a minute ago. So if I have a point P on the vertex, on the parabola, and I measure that distance, those are going to be equal. Okay? All right. Now let's look at the next thing. Okay, so let's see how we derive this equation. So we'll actually go through this one in the textbook. It's pretty short, so not too bad. So basically, we're going to start with the case where the vertex is at 0, 0, and then the focus is at 0, P, and then we have the directrix that y equals negative P. And then we know from the definition, the geometric definition of the parabola, that every point x, y, we just talked about this, on the curve, so this point is equidistant from the focus to the directrix. So these two d's are the same number. They're equal to each other. So using a distance formula, if I subtract, subtract the x's, so x minus 0 squared plus, and then subtract the y's, y minus p squared, and then you take the square root of that. That's the distance for this d. Okay, now this is on a vertical line, so the distance is just going to be, you're just going to subtract the y coordinates, y minus a minus p, which will be y plus p. Okay, So then you set those two distances equal to each other. So basically this d from the first 2 points is x squared plus y minus p squared, square root, just the distance formula. And then that's equal to y plus p. And then from there, we're going to simplify this. So if you square both sides, so if we square both sides, we get x squared plus y minus p squared equals y plus p squared, right? Because we squared both sides. So the square root cancel each other, right? The square and the square root cancel each other. So basically you're just doing that. Let's multiply this out using the square formula. So that's y squared minus 2yp plus p squared. Multiply this one out. Y squared plus 2yp plus p squared. I guess we can switch the p and the y, which I will in the next step. All right, so I can subtract y squared from both sides. Subtract p squared from both sides. See, those cancel. And then I have x squared minus, I'm going to switch the y and p. So 2py equals 2py. And then I'm going to add 2py to both sides. And those are like terms, so I can combine them. And I get 4py. So this is the equation in standard form if we're thinking about a parabola as a conic section. P is the distance from the vertex to the focus, okay? And it's also the distance from the vertex to the directrix. So those are equal, right? And let's see what else. I guess that's it. Okay, so that's our equation for a parabola not centered, where the vertex is 0, 0, and it is a vertical one opening up. Now we can do the same thing for one that's opening sideways, and we'll get, basically you're just going to switch the x and y. So it'll be y squared equals 4px. Okay, so the standard forms of parabola with vertex 0, 0. So table 1 and figure 5 summarize standard features of parabola with vertex at the origin. So we have two types. Vertical axis, the axis symmetry could be a horizontal, the x-axis. So again, when we move this away from being at 0, 0, we're going to say a horizontal axis symmetry. So x-axis horizontal, or a vertical one. Okay, so if it's horizontal, this is the standard form y squared equals 4px. See, for both of them, if it's opening to the right, p is going to be positive. If it's opening to the left, p will be negative. And then for the parabola that's opening up and down, that's going to be x squared equals 4py. Opening up, p is going to be positive. To open down, p is negative. All right, and then so we have our vertex, the endpoints of the last rectum. And notice, if you figure out the distance of the lattice rectum, this is something you should kind of notice. If you went up 2p and down 2p, 2p plus 2p, that's going to be 4p, which comes right here, right? So for all of them. So that's another way to remember what the length of the lattice rectum is. It's just going to be whatever 4p is. Okay, so let's look at their technique, and I'll probably deviate from this, but we'll start out with the first one this way. So first, determine which of the standard forms apply. So figure out if it's opening up, down, left, or right, basically. So once you know if it's a vertical one or a horizontal one, choose the appropriate technique. So we have y squared equals 24x. The way I keep it straight is I think the one from my basic toolkit function, remember y equals or basic toolkit function from way back in the beginning is your basic square function. Y equals x squared opens up. And that's 0, 0, 1, 1, 2, 4, so on. So I always remember if it's x squared, that's opening up or down, depending on what the coefficient is. And then y squared must be the other one. So the y squared is opening sideways, x squared is opening up or down, right? So that's kind of the way I think of it. I go back to this, what I'm really familiar with. Now I can put it in that context. So this is y squared, so this one's opening sideways. It has a horizontal axis symmetry. All right, so use the standard form identified in step 1 to determine the axis symmetry, focus, directrix, all that. So it's this one, it's A. The axis symmetry is y equals 0. Y equals 0 is the x-axis. Set 4p equal the coefficient of x. Okay, so this number here, is 4p. Okay, so we solve for that. So divide both sides by 4, p is 6. So if it's opening sideways, so I kind of just keep that in my mind, this is opening sideways. The vertex is at 0, 0, and it's opening sideways, so that's p, which would be 6, 0. My vertex, 0, 0. Okay, if p is 0, it's opening to the right. If p is less than 0, it's opening left. Okay. Use p to find the coordinates. We just did that. Use p to find the equation x equals negative p. So now we're going to go x equals, or directrix is x equals negative p. And if p is 6, so x equals negative 6. So I put a vertical line at x equals negative 6, right about there. Each spot's 4, so that would be 6, and maybe more like there. Okay, that's my directrix. X equals 6, or negative 6, sorry. Where are we here? Use p to find the endpoints of the lattice rectum. So it's going to be p plus or minus 2p. So we go here to the last rectum, to the focus. And from the focus, I labeled that wrong. It's not p, it's my focus. It's f. Okay, so I go to the focus and I go p and then 2p. So if p is 6, 2p is 12. So I go 12 minus 12. Okay. And then alternate substitute x equals p. So if you just substitute p into the formula for x and then solve it, it'll give you the 2 points that we just plotted the last rectum. So if you put in 6, 24 times 6 is 144. So if you put in 6, 24 times 6 is 144. Square root of that would be, because y squared is 144, square root of it will be plus or minus 12, which is the 2p. So it'll be 6, 12, 6, negative 12. Okay? So you do it either way. I prefer just to count. All right. Now plot the focus, the directrix, lattice rectum, and draw a smooth curve. That's what I did. I like to do one more point too. Is I go from the vertex. I know it's opening sideways, and I like to do 4p, and then the mirror image 4p, 4p. So 4p is the 24, so I'm going to go 24 if I can fit it, right? 24. So that's another point, just to make my curve a little more, let's see, 24. Okay, I can't get, it's in my picture here. So now I'm just going to make a parabola. I'm going to try to hit those points. Oops, we want a curve, not a line. Hopefully you got the idea right there. Okay, and that's pretty much it. So you're going to do that. This is pretty close to the way I actually do it. I kind of do it as I go. So I put in, okay, the vertex is 0, 0. I figure out P is 6. So I go, well, first I figure out which way is it opening. So this is y squared's opening sideways. I set 4p equal to whatever the number is in front of the linear term. Oops. Okay. So let me try that again. So I set 4p equal to that 24. Solve it. P is 6. And then, so I plot. So now, kind of as I go, I plot the vertex. I go plus 6 in the way that it's opening. It's opening to the right. That's my focus. Minus 6. That's going to be my directrix. Then I draw in my directrix. Then I do the 2p, which is 12, and then I go to the focus and parallel to directrix. So plus 12, minus 12. And then I do that one extra point, the 4p. So 4p is the 24. And I go parallel to the directrix, 24, and then the direction it's opening, 24, and then the mirror image on the other side. And then I draw in my parabola. Okay, so I like to do those 1, 2, 3, 4, 5 points for the parabola, plus the focus and the directrix. Okay? Okay, so you could do either way. So my first thing is I'm going to figure out P. So 4p is equal to the number in front of the linear term, right? So it's x squared equals 4py. So 4p is negative 6. I divide both sides by 4, so negative 6 divided by 4, which is, you can do it as a decimal or a fraction, right? Either way. I like the decimal one for graphing, but typically we keep fractions a little bit nicer usually. Okay. I figure out which way it's opening. This is x squared. Remember, I always go back to, I think of my basic toolkit function, y equals x squared as the parabola opens up. So if this is x squared, it's going to have a vertical axis symmetry. The center's at 0, 0, not the center, the vertex is at 0, 0. So the axis symmetry is going to be the y-axis, right? X equals 0. So let's see, what else do we want? Okay, so we want to graph it now. So we know that we have x squared and p is less than 0, right? It's negative. P is negative. So that means it opens, it's x squared, opens downward. Okay, our vertex is 0, 0. So I start there. We figured out P is negative 1.5, so I go down negative 1.5. And remember, if I draw an arrow from vertex to the focus, that's the direction it's opening. See, so it's opening down. And then, okay, so I do P, so I go P, which is negative 1.5, and then minus P, which would be the other direction. So I'm going to have a horizontal directrix. That'll be y equals the y coordinate that it goes through, which is minus P, which is minus a minus 3 halves. So this is y equals positive 3 halves. Or you can say 1.5 if you want. All right. Now, okay, so now I'm going to do the lattice rectum points. So I go 2p. So if p is 3 halves, or negative 3 halves. 2p is, you times that by 2, so the 2's cancel, is negative 3. Or we want just the distance, so the absolute, I should do the absolute value. So just 3. So I'm going to do 3 units. I want to do the absolute value, which is 3. Okay? So the absolute value of 2p would be 3. So I go 1, 2, 3. 1, 2, 3. And notice that lattice rectum is 6 units long, the 4p. Okay, and then I like to do 2 additional points. I'm going to do 4p, 4p. 4p is negative 6. And again, I don't care about the sign. I'm going to, because I do the mirror image. So you're going to do plus 6 and minus 6. So 6, and I'm just doing distance. 1, 2, 3, 4, 5, 6. See, it's opening down, so I'm going to go down 6. And then do the mirror image. 6, 6. And then connect those 5 dots. The vertex, the lattice rectum endpoints, and then those 2 additional points. Now, the book doesn't have you do those additional points. I like you to do those additional points. Just makes the curve a little better. Okay. Let me try that again. I told you I don't like this. There we go. Okay. Okay, and they want us to label the focus. So the focus is, what is the focus? So this would be 0, negative 1.5, or negative 3 halves. The directrix, I already labeled that one. And the endpoint's the lattice rectum. So this point would be 3, negative 3 halves. This one would be negative 3, negative 3 halves. Okay. Okay, on to the next objective. Write equations of parabolas in standard form. Okay, write the equation of parabola in standard form given its focus and directrix. So the focus is negative 1/2, 0. Directrix is x equals 1/2. Okay, I like to do a rough sketch, or, you know, if you have graph paper handy, maybe I do it on graph paper. So let me do this real quick. So the focus is negative 1/2, 0. Negative 1/2, 0. And the directrix is x equals 1/2. All right, let me make this smaller and move it. Normally I just do a sketch. I don't even do a big graph like that. Okay, so we got negative 1/2. Actually, I should make this bigger. Okay, so negative 1/2, 0. So that's my focus. And then my directrix is x equals 1/2. And so the halfway, the midpoint between the focus and the directrix is the vertex. So the vertex is at 0, 0. And remember what I also told you, if you draw an arrow from the vertex to the focus, that's the way the curve's opening. So it's opening to the left. So that tells us p is going to be a negative number. That also tells us that it's going to be y squared equals 4px. And then, so now we just need to figure out P. P is the distance from the vertex to the focus, that distance. So we're going negative 1/2. So P equals negative 1/2. And that's all we need. So we get y squared equals 4 times negative 1/2 x. Simplify that. So 4 divided by 2, so that's negative 2. And then that's our answer. Okay, on the next learning objective, graph parabolas with vertices not at the origin. So we're going to do another one of these shifts of HK. Okay, so if we move the vertex to HK, we're just going to do the appropriate transformations to the basic one. So y squared becomes y minus k squared, and then 4px becomes 4px minus h. So if that one's the y squared that's opening sideways, remember you add the p to the x coordinate, so it's h plus p, k, and the directrix would now become x equals h minus p. And then the lattice rectum points are be h plus p, k plus or minus 2p, and then similar changes for the vertical axis symmetry. Okay? And again, if p is positive, it's opening to the right or up. If p is negative, it's opening to the left or down, depending on which form it is. A, B, C, or D. So all the usual changes. All right, example 4. Graphing a parabola with vertex HK x symmetry parallel to the x-axis. So a horizontal axis symmetry, right? It's going to open to the left or to the right, depending on if P is positive or negative. All right. So again, the way I keep it straight in my head, I always fall back to the basic toolkit function y equals x squared, which is a parabola that opens upward. Right? So if it's x squared, it's up, down. If it's y squared, it's sideways. So you can see this one's y squared. So that's going to open sideways. 4p is negative 16, so we always start with that. We move this up so we have more room. (4p) is negative 16. So this is y squared, and p is less than 0, so it's opening leftward, right? Opening left. So it's going to be like this. So p is negative 4. Our vertex is hk. Now be careful. This is the y coordinates with the y and the x coordinates with the x. So this plus 3, this is going to be h. So remember, you got to switch the sign. So our vertex is going to be hk, which in this case would be negative 3, 1. So x is with x, y is with y. That's what you'll hear me say all the time. X with x, y is y. So my axis symmetry goes through, I'm going to make this one red. So, oops. Okay, that's my axis symmetry. So x equals 1. And then I'm going to do my, okay, p is negative 4. So from the vertex, so the vertex is negative 3, 1. And then from here, p is negative 4. We established it's opening left. So 1, 2, 3, 4. So that's my focus. which is -7, 1. Then I'm going to do my directrix. So 1, 2, 3, 4. So the directrix is here. So let's do this one. I'll leave that one black. So that's my directrix. X equals 1. X equals 1. So basically, x equals 1 is my x symmetry. Oh, this should have been y equals 1, sorry, because that's a y, horizontal is y equals. Sorry about that. Let's see, what else? So that's my first step. I do my vertex. P is -4, negative P. So minus of -4 becomes +4. That's my axis, my directrix. Okay, so that's my directrix. Now I go do my 2p. 2p is 8. Absolute value, remember. So that's 8. So from the focus, I'm going to do 8. So there's 2, 4, 6, 8. And then -8. So 2, 4, 6, 8. And they want us to label those points. So this is a -7, 9. And then this one's -7, -7. Okay. And then that's all the book has you do. I like you to do that one extra one where I'm going to do 16, 16. So that would be at 19, right about there. And then 16, so that would be here. 16, so 3 and 16 would make 19, right there. And then make my parabola connect those 5 dots. There we go. See, did I label everything? I got my vertex, -3, 1, my axis of symmetry, y equals 1, my focus, -7, 1, my directrix, x equals 1, and the endpoints of my lattice rectum. So the endpoints of the lattice rectum. Okay, so that dotted line is the lattice rectum. The endpoints are -7, 9 and -7, -7. All right, so example 5, graphing a parabola from an equation given in general form. So we have x squared minus 8x minus 28y minus 208 equals 0. And we want to identify, label, all that stuff. All right. Okay, so we want to put it in the standard form. So you notice you have just the x squared. So this is going to be a parabola that opens up. So our standard form, or down, depending on p. X squared equals 4py, but then don't forget the hk, right? H. Okay. So I want to get the x squared x term on this side, everything else on the other side. So add 28y, add 208. Now I want to complete the square. So x squared minus 8x plus blank, 28y plus 208 plus blank. So since it's just x squared and I'm not factoring anything, I can add the same number to both sides. So half the middle term, square it, add it to both sides. So 28y plus 224. We're going to factor out the 28. x minus 4 squared equals 28. Y plus, now let's figure out what 28 into 224 divided by 28 equals 8. All right, so now it's in standard form. So let's see, our vertex, remember HK. So that will be equal to, you switch the sign, 4, switch the sign, minus 8, x is with x, y is with y. Gotta keep that in mind too. 4p is equal to 28. Divide both sides by 4, so that's 7. And we also need to know what 2p is for our last rectum, so 2p is 14. All right, now we're ready to graph. Okay, so our vertex is at 4, -8. 4, -8. P is, oh, you know what? I need to, I'm probably going to need a bigger. All right, so 4, -8. Our directrix, well, first let's do our focus. So this is our vertex. 4, -8. And then P is 7, so we do 7 up. So that's our focus, which is 4, -1. And then -7. So let's see, that would be at 15. That would be our directrix. So directrix. X, no, that's y, so it goes through the y-axis, so it'll be y equals -15, and then the x symmetry goes through the focus, the vertex, okay, so that's our x symmetry. Oops, let me try that again. X symmetry. Let me change that one to red. That's our x symmetry. This is a x equals because it's going through the x-axis. That's kind of how I remember it. Usually, sometimes I forget, like in the last problem. Okay, so now, so we got our vertex, focus, directrix. Now we're going to do vertex, focus, directrix. Now we're going to do the lattice rectum points. So we do the 2p. So from the focus, parallel directrix, we do 14. So that gets us to 18. Minus 14. So that's -10. And then the 4p, which would be 28, 28, which is pretty much off of this chart here. So we will just connect them. Kind of know we're going out that way. And then the same thing here. Let me try that again. There we go. Something like that. Something to that effect. And then our endpoints for our lattice rectum are, let's see, what was this one? This is -10, -1. And then this one is 18, -1. All right, and that's it. I think I got everything labeled. Just move this down, just double check. Identify, label the vertex, x symmetry, focus, directrix, endpoints of the lattice rectum. Yep, okay. Let's move on to the next one. All right, and our last learning objective for this lesson, solve applied problems involving parabolas. Okay, solving applied problems involving parabolas. As we mentioned at the beginning of the section, parabolas are used to design many objects we use every day, such as telescopes, suspension bridges, microphones, radar equipment. The parabolic mirrors, such as the one used to light the Olympic torch, have a very unique reflecting property. When rays of light parallel to the parabola's axis symmetry are directed towards any surface of the mirror, the light is reflected directly to the focus. See figure 12. So basically, if we have the sun way out in space and we point this mirror up towards the sun, the rays come in, hit the mirror, and get reflected, and the angle that it gets reflected to reflects it to the focus. So basically, this whole surface area on this mirror, every light ray that hits the mirror gets directed to the focus, right? It focuses that energy, and that's why we call it focus, basically, right? So it's all getting directed to that spot, and then that would catch on fire. So parabolic mirrors have the ability to focus the sun's energy to a single point, raising the temperature hundreds of degrees in a matter of seconds. Thus, parabolic mirrors are featured in many low-cost, energy-efficient solar products such as solar cookers, solar heaters, and even travel-size fire starters. Okay. Also, like if your flashlight, the lens in the flashlight is usually parabolic shape, and then you put the light bulb at the focus, and the light basically turned these arrows around. The light would hit the mirrored surface and bounce, and you would get beams, right? So basically you can do it in the other direction. Example 6, solving applied problems involving parabolas. A cross-section of a design for a travel-sized solar fire starter is shown in figure 13. The sun's rays reflect off the parabolic mirror toward an object attached to the igniter. Because the igniter is located at the focus parabola, the reflected rays cause the object to burn in just seconds. So 2 parts. Part A, find the equation of the parabola that models the fire starter. Assume that the vertex parabolic mirror is the origin. So we can just set it up. We're going to make this at 0, 0. So basically our XY axis would be like that. So from the vertex to the igniter is 1.7, so that's going to be P. And we're making this one open up, so that would be x squared equals 4py. Fine, right? And we just established P is 1.7. So x squared times 4 times 1.7 y. So x squared equals, what's that, 6.8 y. Okay, so that's A. Now B, use the equation to find the depth of the fire starter. So we want the depth from, okay, so it stops right here. And they're telling us the fire starter from this point to this point is 4.5, so obviously that's half. So that'd be 2.75. Oh wait, 2.25. 2.25. And then this is going to be, we'll call it, well, it's y, and that's the depth. So the depth. So we got to figure out what y is if x is 2.25. So we plug it in. 2.25 squared equals 6.8. Then we're going to divide both sides by 6.8. So y equals, and then just punch this in our calculator. Okay, I'm going to use my cheesy calculator here. 2.25 squared is 2.25 times 2.25, and then divided by 6.8. So it's 0.74 0.74. Let's see how many. They didn't tell us how many places to round it to. So about 0.74. So 0.74. We should use the squiggly equals since we're rounding. Okay, so 0.74 were these inches. All right, and that brings us to the end of today's lesson. So again, practice. Make sure to go to the exercises at the end of the section, do all the odds, and preferably, if you have time, do a few more, as many as you feel necessary. All right, have a great day, and I'll see you next time.